Okay, so the next section we're going to look at, we moved out of quadratics, and we're now going to look at the cubics and the quartics. Quadratics are power 2 equations. Cubics and quartics are power 3 and 4 equations. So that's essentially where we're at. If I can just make a note of that. Quadratics, which we've spent a lot of time on now, power 2 equations. What that means is the highest power in the equation or the expression or the function is power 2. Highest power is 2. The look of these equations, they look like ax squared plus bx plus c. That's our function. I might just write it with function notation if that's okay. That doesn't spin you out too much. Fx, function of x, is ax squared plus bx plus c. Okay, so that's old news. We've done quadratics. We've spent a lot of time on them. We're pretty familiar with them, hopefully. We've done really well in the topic test we've just sat. Now cubics, if we can just stay on the same train of thought. These are power 3 equations, as you might have guessed, given that you will have seen cubic meters, x cubed, cube root of means 3. So here our function of x looks a bit like this. We've got one more letter that we need to introduce. Ax cubed plus bx squared plus cx plus d. I might just go back for a second because we're going to look at a second form, or a different form. Now with quadratics we also used the vertex form, which was it was a outside of x minus h squared plus k, where hk was our vertex. Okay, the reason I'm writing that there is because we're going to introduce, for cubics and quartics, different types of, or different forms of those equations. And so for the cubic it will be fx equals a, and you guessed it, it's x minus h cubed plus k, where not the vertex but what's called the point of inflection, and I'll cover that in a moment. We'll talk about what that is, where point of inflection equals hk. Just quickly, I'll erase this, but a cubic, y equals x cubed looks like this. That's y equals x cubed. So these are the shapes of cubic equations. And this thing in here where it does a little kind of shimmy, it goes through here, sort of a concave down shape, and then does a little shimmy, a little movement here, and straightens himself back out and turns into a concave up. That's called a point of inflection. Actually, we might just leave that in place because that's quite nice. That's a cubic curve, and that's a point of inflection. Okay, while we're on a roll, we'll talk about quartics as well, which are power 4 equations. They look like, unsurprisingly, ax to the power of 4 plus bx cubed plus cx squared plus dx plus e. Alright, that's enough. That's enough of that. It has another form that we're going to study, and that is the function of x is a outside of x minus h to the power of 4 plus k. And in this particular instance, that's where the turning point, or the vertex, is equal to hk. Now in a quartic, quartics look like fat quadratics, fat parabolas. So if we've got x squared, we would be used to just doing something like this, going quite steep. X to the 4, well, they got big fat bottoms. They just drag themselves along the x-axis like that. So uni comes, nice big drag along there, and up she goes. So that's y equals x to the power of 4, and that in there is its turning point. It's no great surprise to you. Okay, so they're the basics. What we will look at is just a couple of transformations on that. So we'll just have look at a couple of examples. So let's e.g. sketch the graph of the function y equals x minus 2 cubed plus 4. Okay, so what this tells us is that we have a, what are we calling this? It's a cubic. So a cubic has a point of inflection at hk. So here, our point of inflection is at 2, 4. So we're going to draw ourselves a nice little cubic. But now the point of inflection is going to be up here somewhere. So go across 2 and up 4. That's where we're going to have this thing going on. At 2, 4. So if we had a look at the map, perhaps we should also, let's just draw it. Let's just see what happens. A little shimmy through there, and up it goes. So that's the point 2, 4. It's a point of inflection. And we could find out where the where it hits the x and y axes. Y-axis there, x-axis there. So it's going to hit the x-axis when y equals 0, and y is going to equal 0 when x minus 2 cubed equals minus 4. So that's going to be at the cube root of minus 4, which is at about, if you put the cube root of minus 4 in to your calculators, you would get about minus 0.413. So actually the y-intercept's over here somewhere. I've just got that badly wrong. So it should be doing something like this. I'm spinning through there and doing that. Let's draw this again. I should have got my my points of intersection before I drew it. Never mind. Mistakes are good. So let's get our x-intercept at y equal to 0. So that's 0 equals x minus 2 to the power of 3 plus 4. So x minus 2 cubed is equal to minus 4. X minus 2 is equal to the cube root of minus 4. So x will equal 2 plus the cube root of minus 4, which is about 0.14. It's approximately 0.4. Okay, and we're going to get the y-intercept while we're at it. Y-intercept is at x equal to 0. And x equals 0, if we put 0 in there, we get y equals minus 2 cubed plus 4, that's minus 8 plus 4, which is minus 4. So now let's have another go at graphing this, where we've got our x-intercept is at about 0.4. We've got our y-intercept at minus 4, so down here. And so it's heading up through here like this. And then at 2, 4, draw this through here, and then it does a bit of that, and then heads up. It probably needs to be a bit flatter there, making lots of errors. So up we come quite steep there, then flat. I'm having a absolute shocker. Through we come. Alright, that's better. Just needed it to be nice and flat here. That's going to be my point of inflection at 2,4. This is the point, roughly 0.4, and this is my y-intercept at -4. X-axis, y-axis. Okay, so that's a cubic. Let's have a little look at a quartic, perhaps an example of a quartic. So sketch the graph of y equals x minus 2 to the power of 4 minus 1. So let's find our point. In this case, for a quartic, we have, it's this sort of thing, it's a turning point. So the turning point is going to be at 2 minus 1. Let's make a note of that. Turning point at 2 minus 1. The x-intercept at y equal to 0, so we need to solve that. So 0 equals x minus 2 to the power of 4 minus 1. So if we start to solve this, it's x minus 2 to the power of 4 equals 1. X minus 2 is equal to the 4th root of 1. The 4th root of 1 is just 1, so that's going to be quite nice. X is equal to 1 plus 2, which equals 3. So the x-intercept is at 3, but actually the 4th root of 1 is 1 or minus 1, so it should be a plus or minus 1. Because I can take 1 to the power of 4, I get 1, or I can take minus 1 to the power of 4, and I get 1. So with even powers, there's always two solutions. So we have two solutions here. We have x equals 1 plus 2 or minus 1 plus 2, so it's 3 or 1. Our y-intercept is at x equal to 0, so we put x equal to 0 into y equals 0 minus 2 to the power of 4 minus 1. It's minus 2 to the power of 4 minus 1, which is 16 minus 1, which is 15. Okay, so our y-intercept's 15, our x-intercepts are 3 and 1, and our turning point is at 2 minus 1. So this is going to look something like this. It's going to go through 15 up here, dip through 1, fat bottom, and coming through there. So it goes through 15 here on the y-axis. Y-axis. It's going through 1 and 3 here, and the turning point is at 2 minus 1. And we're done with graphing cubics and quartics. And we are ready to tackle exercise 7a. Now this will be done on Friday, and you should be watching this on a Thursday night. So on Friday, please refer to work requirements for the questions. I will not be in class. I'm off to Hong Kong on an IB trip, so I won't be in class Friday or Tuesday for that matter. So I'll do another video for you to see on Monday night for Tuesday's work. So please take the notes for that and get the work requirements in advance of Tuesday's lesson. Okay, excellent. Have a good exit.